continuing our discussion about trigonometric equations. Okay, so let's say we have a following situation here. Let's say we have tangent of x multiplied times sine squared of x. All right, having this be equal to 3 tangent of x with the restriction that we want x to be greater than or equal to 0 but strictly less than 2 pi. All right. We aspire to solve this trigonometric equation. It's very much like an algebraic expression, you know, with x and y and whatnot, and you solve for one of the variables. But right now, trigonometric functions are involved, and we must get rid of them. We need to peel them away in order to solve for the x that's inside these trigonometric functions. So first things first, we will regroup the terms. We'll subtract that 3 tangent x from both sides to get this. So now, tangent x sine squared x minus 3 tangent x is equal to 0. So now we'll notice that both terms have a tangent of x in common, and that we can factor that out nicely to get this expression. Okay? Now that we have this expression, we can use the zero product rule. Remember from elementary algebra and basically from logic and understanding of numbers that if two numbers a times b equals 0, then that implies two possibilities logically. Either a is 0 or either b was 0, because any number times 0 is 0. So, matter of fact, you can call this tangent of x thing the a, and you can call this other expression in these parentheses the b, and we can separately set them equal to 0 using this zero product rule. So notice that this now implies that tangent of x is equal to 0, and it implies that sine squared of x minus 3 is equal to 0. Okay? So we'll proceed to solve for x in both of these equations. Notice that here on the left-hand side, taking the tangent inverse of both sides, I get x is equal to the tangent inverse of 0. Okay? So now we have to determine what the tangent inverse of 0 is. Okay? We go to our unit circle. This is asking us a question. It's saying, at what angle is the tangent outputting the value 0? So notice that tangent of theta will only equal 0 whenever sine of theta is equal to 0. Because tangent, remember, tangent is equal to sine over cosine, right? So whenever, we can't divide by 0, so cosine can't be 0, but this sine must be 0, okay? So when is sine 0? Precisely here at 0 and at pi. Those are the two locations in which sine is 0. So that is the two locations in which your tangent will output a 0. So x, in this case, this implies that x will equal either 0 or it will equal pi. Okay? Now, don't forget that the period of the tangent function is pi. So when we say it equals 0 and pi, we really mean it equals 0 plus n pi, and it equals pi plus an n pi, where n is an integer, okay? We do that because that is the period of the tangent function. So we will assess what values we will get whenever we plug in values for n. But let's not neglect this equation. Let's finally solve for what that is. We can add 3 to both sides to get sine squared of x is equal to positive 3. Okay, then taking the square root of both sides, we'll get that sine of x is equal to plus or minus the square root of 3. Okay. Now, in order to solve for x, we have to take the sine inverse of both sides. So then we get x is equal to the sine inverse of plus or minus root 3. Okay? So that means that we have two values for x, sine inverse of positive root 3 and sine inverse of negative root 3. So I'll bring that over here. This means x is equal to sine inverse of root 3, and it means x is equal to sine inverse of negative root 3. Okay? So, this is going to be asking us a question. At what angle does sine assume the value square root of 3? That's right. I pause for a moment to think about that statement. Is that ever occurring in the unit circle? Well, absolutely not, and here's why. The sine function has range bracket negative 1 to 1. The range of the sine function is bracket negative 1 to 1, okay? Notice that for the sine function at some angle, evaluated at that angle, for it to spit out the value square root of 3, that would imply that we would exceed this range, because square root of 3, if you plug it into a calculator, square root of 3 is approximately 1.7 with some other digits associated to it. So that is clearly exceeded the range. 1.7 is clearly larger than positive 1. So these values, both the positive and the negative, are meaningless values. They don't exist because they are impossible. All right? So we throw away those values, and we will only focus on these values for x that were extracted from the tangent inverse of 0. So doing that, now I will clear up some real estate. I'm getting, moving this stuff. All right. Now, let's find out what it is for n equals 0. For n equals 0, we have 0 plus 0, which is 0. This is one of our angles. And then we'll also have pi plus 0, which is pi. Here's another one of our angles, and they lie within this range, so we're okay. All right? Now, let's let n equal to 1. This was our n equals 0 results. What about n equals 1? Well, here, now we'll get 0 plus pi, which results in a pi. This is a redundant value. So yeah, that's great. That's nice that we got it, but we had got it earlier. It's redundant. Let's look at this other value, pi plus a pi. This gives me 2 pi. Notice that this has exceeded our range. We right here say that x can be less than 2 pi, but never equal to. If this is a value for x, recall these are values for x. If this is a value for x, then it has exceeded the range. Okay, it has exceeded the restricted values here. And I said range, but it's really the domain, because x is the input, so it's a domain that has exceeded the restricted domain. So we don't actually accept this value, and this value we already had, it's redundant. So the only values that work are 0 and pi. 0 and pi are the only values that work in this equation. So plugging in, for example, if x equals 0, take a look. I would get tangent of 0, which is 0, times sine of 0 squared, which is 0, minus 3 times tangent of 0, which again is 0. This equals 0 minus 0, which is 0. So cha-chink, we've done it right. And you at home, you can go in and you can plug in pi, you will get the same results. So you'll find out that we found the solutions to this equation. And it involved factoring out the common term in the tangent, setting the product of each of those terms equal to 0 because of the 0 product rule, and then solving them explicitly for values of n. Also noticing, I've deleted that information, but we also noticed that stuff where we had the sine inverse of square root of 3 and negative square root of 3, we realized that those values don't exist. On the unit circle, the largest value you can have is 1. So if the sine inverse of something is outputting square root of 3, that means that is not on the unit circle. And so that means those values don't exist. That's why we don't pick those values, and that's why those values aren't solutions to our problem. All right, let's do another one. How about 2 cosine squared of x plus 3 sine of x having this equal to 0 with this interval with the same common restriction on the domain. Let's solve for x here. Okay? So we notice that they don't share a common factor, and we notice that there isn't something that we can do here. What we'll have to do is somehow create a situation that will allow us to solve this equation. It's going to require some creativity. What we can notice is that right here, this is sine to the first power, this is cosine to the second power. So maybe we could utilize the Pythagorean identity for sine and cosine, meaning cosine squared x plus sine squared x is equal to 1. Let us utilize this identity. Notice that if we subtract a sine squared x from both sides, I get cosine squared x is equal to 1 minus sine squared x. So we can plug this in here. Why am I choosing to do this? Well, I'm choosing to do this so that our equation is only in terms of one trigonometric function, namely the sine function. Why did I pick this formula to use? Well, because I had a cosine squared x to be able to substitute. Over here, I didn't have a sine squared x, so I couldn't have substituted that to have it all in terms of cosine. The problem implores us to substitute the cosine. So now that we do that, we'll plug this value into here. So now I get 2 times the quantity 1 minus sine squared x plus 3 sine of x equals 0. Then we get 2 minus 2 sine squared x plus 3 sine of x. Okay? This is all equal to 0. And then notice that I will just rewrite what we have above. So 0 is equal to negative 2 sine squared x plus 3 sine of x plus 2. All of this is equal to 0. This is a great situation to be in, because now our trigonometric equation is a quadratic equation in the variable sine of x. So if we would like, we could use our nice trick. We can use capital T for trigonometry. We can define this to be equal to sine of x. That means that t squared will equal sine squared of x. That means our formula here will get transformed to 0 is equal to negative 2t squared plus 3t plus 2. So all we have to do is solve this equation here. And I like to use completing the square. That's what I'm most fond of, being a pure mathematician. But we could also use the quadratic formula, even though it's more clunky to utilize. But I use complete the square so much, I also need to show you guys how to use a quadratic formula. So t is going to be equal to negative b coefficient plus or minus the square root of the b coefficient squared minus 4 times the a coefficient times the c coefficient, all over 2 times the a coefficient. Okay? So we get this. So notice that this breaks down to, I get t is equal to negative 3 plus or minus the square root. 3 squared is 9. Here we have a negative times a negative, making it a positive. So this is going to be plus something. 2 times 2 is 4. 4 times 4 is 16. So this becomes 16. All divided by a negative 4 here. Okay? So you get t is equal to negative 3 plus or minus square root of 9 plus 16 all over a negative 4. Notice that 9 plus 16 is the same thing as 10 plus 15, which is 25. Okay, and notice that square root of 25 is 5, so this reduces to negative 3 plus or minus 5 all over 4 is what our t is equal to. Okay, so now we're going to have to clear up some real estate. I'll keep our equation over here, and I'll erase everything else. Okay. I'll erase this here as well. Notice that now t plus, when we elect to add, will equal -3 plus 5 all over, and I dropped a negative here, this needs to have a negative, all over a -4. So then this equals +2 over -4, which becomes -1/2. This is our t plus when we elect to add. And our t minus will equal -3 minus 5 all over -4. And this equals 5, 6, 7, 8. So -8 all over -4. This becomes +2. And this is our t minus. So t plus and t minus are equal to -1/2 and 2 respectively. But recall, although I've deleted it, although I've erased it, t used to stand for, that's right, sine of x. T was replaced with sine of x, or sine of x was replaced with t. So we now have to replace t plus and t minus with sine of x. So this implies sine of x is equal to -1/2. And this implies that sine of x is equal to +2. Notice that then taking the sine inverse of both of them, I get x is equal to the sine inverse of -1/2. And that means I also get that x is equal to the sine inverse of 2. Okay? So traveling from here on the board, we go to here. All right? Now, notice that, again, this bottom equation is asking us something that is nonsense. It's saying, at what angle is the sine function when we evaluate it? At what angle does it spit out the value 2? There is no such angle, because the largest value the sine function can spit out, the largest value it can spit out is 1. So this will produce nonsense, because there is no such x that satisfies that. So we're reduced to just figuring out, when is the sine inverse? What is the sine inverse of -1/2? And we go to our unit circle to determine this value. Okay. We notice that sine assumes negative values only in the third and the fourth quadrant. And it will start being -1/2 over here and over here. This is the angle when we add pi over 6 to pi. So pi over 6 added to pi, that becomes pi plus 6 pi all over 6. This gives me 7 pi all over 6. So this is at 7 pi all over 6. And over here, this is going to be at 2 pi minus pi over 6. I get 2 pi minus pi over 6. This is equivalent to 12 pi minus pi all over 6. This becomes 11 pi all over 6. Okay, so let me, before I move on, explain this reasoning. Over here, the sine value is 0. And whenever we move the 30, 50, 50, 30 rule, whenever we move 30 degrees, which is in radians, pi over 6, we add a pi over 6 to pi. And that's how we get that value, 7 pi over 6. At this special angle, sine is -1/2, and cosine will be -√3/2. If you've watched my unit circle videos at the special angles for sine and cosine. And over here, the same concept. Over here at this point, sine is 0. But dip 30 degrees below that value, and your sine is at -1/2, and your cosine being at +√3/2. So that's how we got these values, okay? So our answer is going to have a 7 pi over 6 and an 11 pi over 6 involved in it. But recall, what is the period of sine? That's correct. I hear you at home yelling that it is 2 pi. So because the period of sine is 2 pi, we have to say that our x is going to be equal to 7 pi over 6 plus all integer multiples of the period of sine, and x is equal to 11 pi over 6 plus all integer multiples of pi. Okay? We see that? Now, we will plug in values for n, starting at n equals 0. We get the trivial values that we had earlier, and 11 pi over 6 and 7 pi over 6. Okay? These two values are definitely good values because they are below the numerical value of 2 pi. But whenever we let n equal 1, notice what we get for this guy is 7 pi all over 6 plus 2 pi. And any number that is greater, any number added to 2 pi is a number greater than 2 pi, then that exceeds our domain restriction. So this is not a value that we want, okay? That would exceed our domain restriction, so that is not a value we want. And even when we plug it in for here, we get 11 pi over 6 plus 2 pi. Any number that's positive, you add it to 2 pi, it's going to be greater than 2 pi, then that exceeds the domain restriction. So we don't want that either. We don't want this either. Notice this is all because I'm replacing n with equal to 1 here, n equal to 1 here. Okay, so the only values that work are 7 pi over 6 and 11 pi over 6. And we've actually solved this equation here.